fix it actually. And then
does that work?
no, unfortunately no. I don't know how to fix it.
Can you pass the microphone there so that people can hear you?
Hello.
Can you hear?
Can everybody hear me? Okay. Does it work now? Can people hear me? Should I put this somewhere on my tool?
People can hear me.
Here?
Okay. So, with this video comment, welcome everyone. We are very happy to have Andreas Bauer from Freie Universität Berlin. He'll be speaking about his very interesting recent work on Tensorial TQFT and disentangling modular Walker-Wang models. Let me remind the audience, please feel free to ask questions and interact with Andy during the talk. Yeah, so let's start the program. Andy, you have 90 minutes. You have 90 minutes.
Thank you.
Thank you.
Thanks for the introduction and thanks for the invitation. It's a great opportunity. So I was asked to talk about something related to this paper down below there, which is about a certain class of models of topological order in 3+1 dimensions, named Walker-Wang model, and a certain subset, namely the modular ones, are conjectured to be actually in a trivial topological phase. In this paper, I show this for a subclass of those models explicitly by constructing invertible domain models to vacuum, or equivalently constructing a disentangling node unitary circuit. And my plan for today was to, well, not so much talk about the precise results of the specific paper, but more to give you a general introduction to the general methods and definitions that I'm using in this paper. And those definitions are, well, similar to definitions that people commonly use, but they're at the same time also quite different, and I refer to kind of style of defining things with tensorial TQFTs. So now, the broad area of this paper is the study of topological phases and the classification via algebraic structures, and in some way that captures the phase at a fixed point of renormalization groups, so at a zero correlation length. So what are topological phases? Topological phases are equivalent classes of locally physical models with many degrees of freedom. And basically there is 3 different types of such physical models. On the one hand, there's quantum field theories, which are often used in high energy physics. Then in condensed matter physics, we use Hamiltonian models, many body Hamiltonian models. Here, like in quantum field theories, both space and time are continuous. In these many body Hamiltonians, we have a discrete space with discrete degrees of freedom, but a continuous time evolution. And the third type of model is given by what I call discrete parking rules, where all of the dimensions are discrete to both space and time. So one area where this is commonly used is classical statistical physics. So for example, the classical partition function of the classical easy model is described by such a discrete parking rule. And of course, now the classical easy model does not have any notion of a time. The parking rule is purely in space. However, you can also use such the discrete path integrals in a space-time, which is like quantum models. And this is what I'm going to do. So this is my preferred type of model because it's very simple and it's well-defined. And as we will see in the first talk, all these algebraic descriptions of topological order will in the end boil down to having a discrete space-time. Okay, so when people talk about topological phases, they usually do mean the phases of quantum systems. So the quantum phases which describe the ground state properties and not the time evolution of a model. And the ground state you get by applying imaginary time evolution, so by cooling down the system. And in order to get really the ground state and not some thermal state, you really have to go to scale to go to an infinite imaginary time. At the same time, you also need to scale your space lattice to have a well-defined thermodynamic limit and to be at one place in the first place. So the correct thing to scale up to look at is the space-time, but the space-time has an imaginary time component, so it has a competing signature. Okay, so now how do you actually define such a discrete path integral? So we start by putting some regular lattice on our space-time, for example, a square lattice for a two-dimensional space-time, and then we associate variables and weights in different places of the space-time. For example, we could put a variable on every edge and a weight on every edge. And now the value of these variables, the weights are just real numbers or quantum mechanics and complex numbers. So the value of these weights depend on the value of the variables in small surrounding regions. So for example, the value of the weight of a cat may depend on the variables of the surrounding edges. And then the path integral is defined by a simple state sum. That means that we sum over all different configurations of all the variables distributed over the lattice. And the thing we sum over is the product of all the weights for these given configuration of variables. So another way, an alternative way to describe this discrete path integral formally is via tensor networks in space-time. So here below I depicted a tensor network living in a two-dimensional space-time. And I also put some boundary conditions here in blue, and I also put some extra tensors with extra open indices here in red. So if you contract this tensor network, what you would get a two-point function. So for people who are not familiar with tensor network notation, in this diagram, every of these tensors, every of these boxes or shapes represents one tensor. Every index sticking out of one such box. Every line sticking out of one such box represents an index of a tensor. So by tensor, I just mean a multi-dimensional array of numbers. And if I connect two of these boxes by a line, that means that I contract over these two indices of the two different tensors. Or in other words, I perform an Einstein summation or a partial trace of those parent indices. So now, if you do evaluate this tensor network, then what you do is you have to sum over all configurations of these bonds. And the thing you sum over is the product of all the tensor entries for this configuration of bond indices. So you see that this is nothing but a state sum too. But it's kind of a specific type of state sum where every variable only appears in two different ways. So state sums in first sight would be more general, but actually you can also replace any state variable by a sort of delta tensor, then you obtain a tensor network. So they're really two equivalent ways of doing the same thing. And this language is kind of a bit nicer. You can reason a bit about things a bit more formally, and you have this nice diagrammatic way of representing things. So now I'm not interested in any discrete path integral, but I'm interested in ones that host topological space, and I want to classify them at a fixed point, so at a zero correlation net. And the thing I'm going to use to classify those like this one single unique property, and that is that these path integers are topologically invariant. That's where the name comes from. So how do you formulate this in terms of discrete path integers? So to define topological invariance, at first you need to not only put my discrete path integral on regular lattices, but I also need to be able to put it on arbitrary, irregular grids that live in arbitrary topological manifolds. And the standard thing to do here is just to put it in arbitrary triangulation manifolds. So here I've shown you a triangulation of a two-dimensional manifold, here in orange. And now on this triangulation, you can put a tensor network. And you, for example, in this example, we do this by putting one tensor at a triangle, and then we have one pair of contracted indices for every adjacent pair of triangles. Okay, so now how do we implement topological invariance? So since we want to describe fixed point models, this topological invariance holds exactly. And we propose this by just taking like a set of local changes of the lattice, which do not change the overall topology. And then we look at how does a tensor network change when we do this change of the lattice. And then we just equate the tensor network before changing the lattice and the tensor network after the changing the lattice. So, for example, in this two-dimensional simple triangulations example, there are so-called Pachner moves, which are known to be able to perform any two triangulations into each other, exactly if the two triangulations describe the same overall topology. So those are really a discrete version of homomorphism, topological invariance. And one of these patterns is given as depicted here. So we take two triangles which are separated by a horizontal edge, and we swap them for two triangles which are separated by a vertical edge. So in order to apply this move to some triangulation, we just look for two triangles that look like the left and replace them with two triangles like the right. So if we now see how the associated tensor network changes, then we'll see that, well, in the tensor network, we simply exchange like two tensors that are contracted with a vertical bond by two tensors that are contracted with a horizontal bond. And now we simply equate these two tensor networks. So that doesn't mean that the diagrams are the same, always the other one. What I mean by this is that if we contract these two tensor networks, then we get the 4-index tensor on each side. And if we demand that we impose that these two 4-index tensors are the same. And then if we impose this, then the pattern will really manifest the locally topologically invariant. Okay, so what we get is one 3-index tensor and one equation for the 3-index tensor. And every 3-index tensor solving this consistency condition will be a fixed point model of 1 plus 1 dimensional topological order. And this is known as two-dimensional lattice TQFT, and it was developed in the early 90s. And if we look at these equations, then we see that they are equivalent to some well-known algebraic structure, namely special Frobenius algebras. So in order to see this maybe quickly, if you take this 3-index tensor and interpret it as a bilinear map from two of the indices to the other, then this is the multiplication of an algebra. And now this equation exactly defines the associativity of this algebra. Now there's obviously many little details that are neglecting here, but if you take into account these details, the equations become a little bit more complicated, more equations, and then what you get is this special Frobenius algebra. There's something very close to it. Yeah, lattice TQFT and state service, same thing. Exactly. Okay, so let's quickly look at the same thing in 3D, really completely analogous. You might take triangulations consisting of tetrahedra of 3 manifolds. Then we associate to every tetrahedron one 4-index tensor, so which shares bond with all the adjacent other tetrahedra. And now a Pachner move in these 3D triangulations one example for a button is looking like this in orange. So on the left-hand side, we have the two tetrahedra that are glued on top of each other, separated by this like horizontal, this triangle in the horizontal plane. On the right-hand side, we have the same volume, but we now have an edge going through the middle from the bottom vertex to the top vertex. And this triangulation now consists of three tetrahedra that kind of surround this like edge in the middle. It looks like a bit like decomposing an orange into its pieces. And so when we look at the tensor networks associated to both sides, then on the left-hand side we have like two of these four index tensors contracted along the invertible one. On the right-hand side we have like three of these tensors correspond to the three tetrahedra, and they kind of contract in this ring-like way. And now I simply equate again these two like tensor networks on both sides and demand that we get the same 6 index tensor on each side.
And so the left-hand side, the two tensors integrated along like kind of the middle.
Yeah.
On the right-hand side, along the
so there's three tetrahedra, and each of them share one, and each pair of them is connected by one face. So they kind of go in a circle.
What is three?
Yeah, three.
So how does that back?
Two.
And each of those dots is on the center or relative to the middle.
Huh?
The dot is put in the middle of the tetrahedra.
Yeah, you can geometrically imagine it that way, yeah. That's what I was trying to depict here. Not very well, but yeah, exactly. Yeah. Okay, so again in this example we get one 4-index tensor, one consistency condition for the 4-index tensor, and every 4-index tensor obeying this consistency condition will be a topologically invariant path integral and can be used in a way to classify tuples one-dimensional topological order. So now, this example does actually not correspond to anything that is like known in the literature to my knowledge. However, you can kind of go to a more fine-tuned version of this. And I don't really have time to explain it in detail, but the way to do this is utilizing sort of computation to get from a 3-dimensional path integral to a 2-dimensional one. Then you use the fact that these 2-dimensional path integrals, they correspond to special Frobenius algebras. You use the fact that those Frobenius algebras, they are classified, they are very simple, they're just isomorphic, like all of them are isomorphic to a direct sum of full matrix algebras. And you use this classification result and sort of plug it back into the 3-dimensional state sum. And what you then get is this like more fine-tuned version of the state sum, which is equivalent to what is known as a derived Führer state sum. So this is now a state sum that also has variables at the edges and not only at the faces.
In typical.
Yeah.
You put the degree freedom on the vertices or link or equal and also on the quadrate. Where are the common degree freedom you use?
So in this like language I presented it to you first, there's only like a tensor network living in the space-time, but if you view the tensor network as a state sum, then well, the variables of the state sum would be these effective indices, and they correspond to all the faces. So this would be equivalent to having a state sum with variables in the faces and weights of all the tetrahedra.
So it's like two cycle, with two simplex.
Yeah, variables in 2 simplex, weights in 3 simplex. Exactly. It's kind of the simplest form of a state sum that captures all topological faces with the topological boundary as well. Yeah.
How do you do this?
Yeah, so what you do is actually a like geometric map. You use a map from 2D triangulations to 3D triangulations, which topologically is a suspension. So actually, this picture actually illustrates this map. So if you have a triangle, then you replace it by one tetrahedron on top and one tetrahedron on the bottom. Which topological is a suspension. And then you like pull back the state sum along this geometric map. And this like defines from your 3D states and 2D state sum. And then, yeah, but there's a bit more to it, sorry. but that's the essence of how to arrive at this like slightly more refined version.
But naively, if you put the quantum is a variable and you read it on the syntax, it looks like you are writing TQFT in a continuous version of like expressing in terms of the P field or Foucault field or Foucault cycle. So in that case, it seems like you are able to construct certain kind of TQFT, for example, some kind of a different co-cycle twist consistent with your particular conditions, and that twist will be specific for the B field, regular B field. There will be two forms or two co-cycle types.
Yeah.
But
So
instead of the one co-cycle, so there will be another somewhat back-up different type of description history there, right?
no. So the variables, they're really not they're not elements of the group. So this configuration of variables doesn't have nothing to do with a two co-cycle.
Okay.
Well, except for it also lives at the faces, but it's not group elements, and there's no constraint that for every tetrahedron the sum of these group elements needs to be identity of the group. Yeah.
But can you maybe you will talk about that, but at some point can you relate the construction to some version of the local homology type of TQFT, or maybe even higher group version of the local sector, the field type of version.
Yeah. So any discrete gauge theory, so any gauge theory with an action that is based on a homology operation that can be captured via such a state sum, right? You just have the variables such as represent the co-cycles. Well, it's an I co-cycle in the variable located at the I simplices, and then there is one weight that is just the co-cycle constraint. The sum of like the boundary of the co-cycle needs to be 0. They live at the I+1 simplices, those constraints, but they're just tensors which are 0 or 1. And then you also have this action, and the action lives at the highest dimension at the nth place in n dimensions. So any of those things is contained in there. Cool.
Would that be even more explicit or investigation? When you compare it to other types, maybe it's like a common novel version of the state sum model or homology type of state sum.
So yeah, so a quantum double is so just a 3-dimensional ordinary quantum double. There will be a state sum where you have like variables on all the edges, some of one co-cycles, and then you have a weight on every triangle, which is just a weight that is like 0 if the group elements sum to identity, do not sum to identity and 1 otherwise, and then you have a weight in every tetrahedron, just the 3 co-cycles that determines the action. And so that defines your state sum. You can reshape the state sum and bring it into this form if you want. So you can, for example, for every variable at an edge is replaced by if you write it as a tensor network, it's replaced by a delta tensor. So you get a total tensor network, and then you just reshape this tensor network further. Put one delta tensor and split it up into a ring of delta tensors. And now the delta tensors in this ring, they are associated to like the tetrahedra surrounding this edge. So now you don't have anything on the edges anymore, you have the tensor network on this form. That's roughly how we would do that.
So, and I understand this distinction contains the case of backup reason.
Yes.
And also using the backup reason for the group to the case that you put on the link variable, you can also put it on the top page. In that case, this is the local content node.
Yeah.
Okay.
Cool. Okay, so this definition of topological particles can also be extended to include topological boundaries, so you can not only classify the bulk, but also the topological boundaries of the bulk, or any other sort of kind of lower dimensional manifolds that are sort of embedded or defined interfaces between things, like the main walls and other sort of defects. So for the simplification of a boundary, let's look at an example in like 2 space-time dimensions. What you do is you simply define your path integral on arbitrary triangulations with boundary. And then, well, in the bulk, you just, as before, put one tensor in the triangle, but at the boundary, so one way to define this path integral is just to put one different tensor at every boundary edge. So now you define your path integral on arbitrary manifolds like triangulations with boundary. Now you again want this boundary also to be topologically invariant. So this you have to define additional moves that can also define the triangulation of this boundary without changing its topology. So one possibility to do this is by what I call here boundary coupling moves. So in 2 dimensions, boundary coupling moves would, for example, be to exchange one boundary edge together with the adjacent part of triangle and replace this for 2 boundary edges. So for example, if you would apply this move to like one boundary edge here in the adjacent triangle, that would mean you just remove this bulk triangle from the bulk. And now instead of one boundary triangle, you have 2 boundary triangles. Instead of one boundary edge, you have 2 boundary edges. And again, you can just look at the corresponding tensor networks associated to before the move happened and after the move happened. And then you get an equation between 2 different tensor networks, which are formed by 2 different tensors. And then the solutions to this equation will give you 2 tensors, which define a topological fixed point model together with the topological boundary. Yeah.
Okay. So, the space sum usually people classify a path interval, right? But a tensor network usually classifies some state.
Oh no, no. Well, often when people talk about tensor networks, they mean these MPS, matrix product states, and projected entangled pair states. So this is very different from what I'm doing here.
Okay.
I consider a tensor network that lives in space-time, and this doesn't even have any open indices.
Okay.
So normally these MPS or TAPs, they have open indices, and if you contract them, then the tensor you get at the open indices is a state. But here we do not have open indices. The tensor network as a whole, describes a path integral, except for when we just cut off the tensor network somewhere. Then this corresponds to a spatial cut, and then we get open indices at the spatial cut. But the main difference is really that these tensor networks are 1 dimension higher. So they live in space-time, whereas PAPs and MPS, they live in space.
But you're saying if you agree that into a tensor may not be a group element or something, can you just specify what input you're considering?
What input?
Yeah, just those things that you the data for the tensor, what are those things are you input on maybe some categories, different categories? What's exactly the data?
So that's kind of the point of the talk, to shift the perspective a little bit. So I do not start with some kind of category and use it as an input for some training I construct. I directly write down the model, and I get an algebraic structure. And let's say the model is this algebraic structure. So, because fundamentally, what is a fusion category? It's also just a finite set of tensors with a finite set of tensor network equations, and you can't actually classify it. And fundamentally, what I get from this framework is no different. You get a finite set of tensors, finite set of tensor network equations, and this defines an algebraic structure. And in both cases, you can classify it. So there's not really a reason why.
Will you at least specify what's the number, what kind of input? Maybe usually some kind of a ring or field, maybe a real number or complex number or what? Or the integer, or what's the thing that you want to encode inside?
Oh, so the tensor is really just a multi-dimensional array of complex numbers.
Complex number.
I mean, you could define it a bit more abstractly and say these are string diagrams of a symmetric monoidal category or actually complex closed symmetric nodal categories, so they're bad, for the type of matter you consider. So if you do like bosonic quantum matter, then those are really just like arrays of complex numbers. If you do like things with a time reversal symmetry that's class 1, then you could pick like real entries and choose to not have an orientation. How you could implement this. If you want to describe fermions, these diagrams would actually correspond to kind of supertensors, so tensors that are set2 graded, and also depend on like the ordering of the indices. So there is some choice here, but for bosonic matter, which you certainly for the talk, it's just really arrays of complex numbers. And I choose all these fundamentally to be finite, which seems to be able to capture all topological processes and can capture calculus.
So in the 3D version, the quantum version, can this capture maybe S2 unlevel tensor? That would be Cairo, probably not.
Yes, that's one problem. I'm gonna get to in a few slides. So this approach, so far, there are only examples for non-Cairo equations. So this approach captures into those one dimensions.
How about S2 to level K times S to level minus K?
That would be non-Cairo. That would be in there. Yeah.
Okay.
So anything that has a topological boundary, or that has a gap boundary, anything can be done. It's not a problem. But the converse is not really known yet, or at least.
And I think you emphasize there's something about the pattern move that you write down has to be seen in your head. But you emphasize what you emphasize that again. What is weird? I think you said something that is not seen in the literature before.
Oh well, no. People just I don't think this like simple form of the path integral. This does not correspond to any like known algebraic structure in the math literature, at least not to my knowledge. But this more refined version you can derive from it, this Tensorial heuristic. So this corresponds to fusion categories, which
what is the more we can kind of conjecture? But how can you define some tensor equations?
Yeah.
And those don't belong to
yeah, exactly. So they're not fundamentally different from fusion categories or Arrhenius algebras, but it's just not something that has been studied in math textbooks.
So what do you mean by the more refined version?
By more refined means that like that. So this is very simple. You just have, as a state sim, you just have one variable at every phase and one weighted at every integral. And this is more complicated, but at the same time, like if you have a solution, if you have a concrete model, then it's easy to describe in this more refined form. So you need to specify less numbers. So this more refined form is, for example, have also variables at the edges and variables at the faces, and this weight at a tetrahedron. This will be given by a 10-index tensor. 6 of these indices correspond to the 6 edges of the tetrahedron. 4 of them correspond to the faces. And this 10-index tensor is exactly the F tensor of the fusion category.
And I still didn't hear clearly, so I think what is known and what is new? Is it separate?
Oh, all of this is basically known stuff. It's just a slightly new way of presenting it.
Yeah, which is quite new. If you want to stay with make that statement, I think you understand.
So, like the thing that present in a slightly new way is that I just consider tensor networks with one tensor associated to every tetrahedron, instead of considering a more complicated state sum. I consider this very simple tensor network path integral. And what I get out from this is the same classification that is already known.
So in short, this tensor network path integral plus mu. That's the thing. The tensor network path integral.
Yeah. Okay. Yeah, but it's really all equivalent. Cool. Yeah.
Just to clarify, this talk touching memory, are you just down or down another question? Like what are those boxes pointing at?
Oh, so all shapes in those diagrams are tensors. So
Right.
these round circles are tensors. And actually all of these large tensors, I maybe didn't mention this, but so the model is uniform, so all the tensors you can divide in the same. But these boxes are different from the circles.
And what is it, like what does that represent?
So if you think of the tensor network as theta, then those would be the weights of like the tensors given formed by the weights depending on the surrounding states and variables. So for example, if you would use the tensor network to describe classical statistical physics, these tensors would be the tensors forming the different balls of weights.
And then what's the deal with invertibles on the tension? Are those on the
Yes, but those are just because I was like too lazy to continue drawing this lattice. So normally I would put this kind of on a closed triangulation and there would be no open indices. But if I do cut it off, then I do get these open indices that look like the boundary, and those open indices correspond to degree freedom. So or they could also define a state living on this spatial surface. Cool. So in the same way, we could also define anyons. So anyons are just these tensor integrals where I have like embedded word lines, and along these word lines, I just put some extra tensors, like connect these extra tensors maybe with some extra indices, and then I demand that these extra tensors, together with the tensor of the surrounding part, they fulfill some tensor network equations. And applying these tensor network equations allows me to like move around these world lines arbitrarily. And this way I get like a finite set of tensors with finite set of consistency conditions, and those now define like path integrals that include anyons, like anion world lines.
Are these anyons like showing part operators or even factors?
No, so matrix product operators viewed in this formalism, they would be, so first of all, like caps describing topological ground state. In this formalism, they will correspond to actually not the topological plane itself, but to topological boundaries of the space.
I think the wall line itself is made of tensors, right?
Yeah.
He's adding a bunch of tensors to the network.
Yeah, basically. Yeah.
And are they how? Do you have an example in law or in anion lines of and tensors define your path integral and tensors define your wall line insertion with a path.
Oh yeah, they share indices. Yeah, it's not a disconnected tensor network or a wall line that's disconnected. They are connected. Yeah, that's actually. Yeah, but I do not have a picture here for that. I just wanted to mention that as an example.
You don't understand whether there are special like one and two representation. Do these anion tensors, are they the same type of tensors as the one with path integral in the sense that there's not some special like one and two representation on those?
Yeah, they're plain tensors.
Okay.
All of the things here are just plain multi-dimensional arrays with numbers in.
So Andy, there's a question online.
Oh yeah.
So if you turn on the speaker, the player is like able to see on the screen.
Hi. Yeah, can you hear me?
Somehow, somehow my laptop speaker is not very loud.
Okay, let me type it into the chat.
Can we try on your laptop?
Well, we cannot turn on both. Let's see. I have
Because mine, the sound seems to be basically bad, unfortunately, and I also. Let's try. also strange you cannot access the meeting anymore. Like I do not see that.
I tried to type it into the chat, Juven, so hopefully you can just read it.
I tried to randomly. Can you repeat? Could you repeat?
Oh yeah, so I tried to type it in the chat, if that's easier.
What's the problem? I don't know. I think it's my laptop is just.
Or don't worry about it.
Should we try with your laptop and just turn the sound off of mine?
I think I can
Don't.
try with my voice for a couple of hours.
Yeah, I think it can turn off the audio.
Yeah.
Hello? Yes.
So can you hear me now?
Please ask. Thank you.
Yeah. Okay, so I was wondering the following thing. So what I understood from what you said so far is basically you write down a tensor network, you impose like invariants under these Pachner moves, and then you get out some classification. And so it's, it's kind of like, it's a little bit like the string net construction, right? Where you say, look, I'm gonna have something, it's gonna be invariant under these moves. In that case, it's a wave function. But so in that construction, like the data that you need to specify string operators is additional data beyond the data that you need to just specify the topological vacuum. And so I was wondering, you said you just write down special tensors and so on, but don't they also sort of need somewhat different consistency conditions so that the anion lines can sort of slide around and so on? Or does that work differently here?
Barely. Sorry, it's a bit hard to.
Why do you need this? Is it your laptop? Where's the sound? You want me to sign up that? You only need one word from audio, right? You want anyone that works.
Yeah.
I also don't want to take, I don't want to derail the meeting, so it's not in.
Sorry, I could only understand half of what you're saying, unfortunately.
Okay. Hi. So
let me read what you wrote in the chat for now.
Yeah, that's right. Good. Let's do it on the chat.
So so that's exactly what I would do.
I think you want to compare with string net.
Yeah.
It's from Fiona, I think.
Cool. So here I'm basically doing, like in stringnet models, you impose the topological invariance on the level of the space. So you can assume that by applying certain like f moves, the state gets transformed in a certain way, and you have coherences between these f moves, and they just correspond to those coherences are the consistency equations for the tensors in the states and path integral. And so now if you want to calculate anions in the stringnet picture, then you would consider something called the tube algebra, and the anions would correspond to the representations of that tube algebra. And this is exactly what you get if you would define anions in this way that I just very superficially told you how to do this. So if you would do this in the state sum, then you would define tensors along lines, but the lines would actually be sequences of tube-like volumes embedded in your triangulation. And the topological invariance of moving around these sequences of tube-like volumes, if you look at the equation, then you will find that what defines these equations is exactly representations of the tube algebra. So this way. And the string operators that move anions around in string net models, they will be just taking those tubes in space-time and putting them in a spatial direction. So because it's Euclidean space-time, you can put those tubes in any direction you want. And if you kind of glue these tubes onto your spatial lattice, then those are just operators, right? which have this split a stringlet form, and those are the stringlet operators that transport your anions. Yeah.
So there's an audio issue.
Let's see. So, Yona, right? Yona, is it clear?
Did you? I think
Yes,
she
yes,
signaled
I
that
gave him the
she
thumbs up.
She was happy with the explanation.
Thank you
Yeah,
very
we
much.
should try
Yeah.
to fix
Yeah.
the audio somehow.
I guess since you are the person you are voicing that, I guess you can use the same one, otherwise there will be echo.
Okay, I can try to quickly. So somehow I cannot. Somehow I cannot access the.
I think let's see. I think there should be some choice.
Yeah, I cannot see the. I think in order to see this, I need to stop sharing for a second. Okay, now I can see. Now I can see my ordinary screen video.
There's something here. You can choose maybe this one.
Is it that thing?
Yeah, this.
Maybe we stop. Just exactly.
That's the simplest. That's the simplest.
Well, my computer is also very slow. That's the issue.
Yeah,
But are you able to restart? And let's do a super.
Very sorry, we're having some issues with Zoom. We'll be back in a moment.
Over there.
Thank you for staying. I think we are back. So can you hear me? Can you hear us? Yes, great. Thank you. So we are back. So let's continue then.
You still need to sharing.
Yes, I can make a call as well. Yeah, right. Yeah. Yes.
Okay, can everybody see my slide? Okay, so sorry to interrupt. I'm trying to connect the speakers to the laptop and then flash. So I hope I can make you actually hear me now when you ask a question. Okay, so I think it stopped when I was explaining how to also like implement algorithms, but just saying like sort of like special development, special tensors, and exposing like topological workarounds. Okay, so there's one other like kind of slight generalization you can make in addition to introducing any sorts of like defects. You can also demand some extra invariants, so some invariants just beyond topological invariants. So you could impose some additional moves which do not like leave topology invariant, but you could impose some additional moves which can change topology. And one simple example for that are so-called surgery operations. So one surgery operation I depicted here. It's an operation you would apply to two-dimensional space-time manifolds. And you would like, for example, cut out a little cylinder, like shown on the left, so like an annulus whose boundary consists of two circles. And then at the same two circles, you would now glue in two disks instead. So that's a move that changes the topology. And if you impose like all such surgery, like invariants under all such surgery operations, then what you get is you don't get a classification of topological phases, but only of invertible topological phases. So invertible phases are those where when you stack two layers of the phase, or actually one of them is like complex conjugated, then you get a trivial phase. So maybe you can like see this a bit from here. So for example, you have like two layers of this two-dimensional space-time, and then you apply this move from the right to left by taking one of these disks from the top layer and one from the bottom layer. Then the effect of applying this move would be kind of to punch holes everywhere in your double layer system. And then we can apply the opposite move to like cut some of the arms you get. And then, well, you get like a disconnected set of spheres. So you can see that by imposing this move, this means that a double layer can be transformed into something that is trivial. Another such like extra invariance, which is very important for topological phases, is that if you consider domain walls between two different topological path integrals, so like lines or like interfaces, like between these two path integrals that are invariant under topological moves, so they can be arbitrarily moved around by some tensor network equations. Now, for these domain walls, you might impose some extra
moves, one of them I've depicted here. And those moves make the domain wall invertible. Invertible domain walls are important because they define the equivalence relation on topological path integrals inside this fixed point wall. So two topological path integrals are in the same phase if there exists an invertible domain wall between them. You can take this as a definition of like topological phases of these highly constrained fixed point models.
Do we include global symmetry here? Can this invertible domain wall be SPT?
Can the domain wall be SPT? But yeah. But you can do the whole formalism. All of it you can just do by imposing a symmetry, like an onset symmetry to all your tensors. So that means you, instead of using like a tensor is just a multi-dimensional array, you now use a tensor is a multi-dimensional array together with a representation of the symmetry group at every index, such that this tensor is invariant under this representation. And if you do that, then you get like SPT and SET phases. And the SPT phases are, well, they are exactly the invertible SET phases.
Is that invertible domain will include SPT? Can
Yeah.
that be non-trivial SPT? Do you identify a phase?
Yeah, this definition is like also works if you have fermions or if you have symmetries. Yeah, that works for any like type of topological matter.
Would you call the phase on two sides even by invertible domain will being SPT as the same or different?
Sorry again?
Would you call the phase on two sides of the invertible domain where invertible domain is SPT? Would you call that the same or different phase?
What do you mean by the invertible domain wall is SPT?
SPT is invertible. Invertible domain will be in SPT. Would you call the two bases on the two sides the same or different? Because you are saying that statement.
No, I don't quite understand what you mean by the
phase on two sides different by invertible domain.
Yeah,
can be identified.
Yeah, so that is what I use as a definition of a phase.
If the invertible domain will become being just SPT, would you call that still?
Do you mean when the two phases are SPT phases?
The invertible domain will be SPT.
But that's not really a thing, right? I mean, you could impose. No, but like SPT means that if you do not enforce symmetry, then you have a trivial phase. So I do not understand what you mean by the domain wall itself to be in an SPT phase, because like there's no notion of a trivial phase for a domain wall, right? If the two phases, if the two models of the two sides of the domain wall are non-trivial models, then the domain wall itself cannot be trivial.
But you can define the phase classification also on one whole dimension, right?
Yeah, so that's effectively what I'm. Yeah, you can define phases of the bulk, phases of the boundary, and those are all defined by kind of like different versions of these invertible domain walls. So you, in addition to defining invertible domain walls between two different bulks, you could also define invertible domain walls between two different boundaries. No, I don't think so either.
That is SPT in that dimension. Would you still count the classify the two sides of phase being same or different?
Yeah, I'm sorry. I really.
I guess probably they're still the same.
Yeah, I really don't understand what you mean by that. The domain wall is an SPT phase.
Suppose the bulk is d dimensions.
Uh-huh.
Domain wall is d-1.
Yeah.
You can still consider d-1 dimension domain wall as just d-1 dimension SPT. Right.
How that?
Why not? That's possible. It's also invertible. It's gap, and that possibly preserve the whole symmetry of also the bulk, right?
Yeah, maybe you're talking about kind of the idea of like gauging stuff. So the idea that, but there's like if you have like a group quantum double, then you can interpret the boundaries of the group quantum double. They're kind of in one-to-one correspondence with SPT phases of this group. No, that's not very okay.
Yeah, I guess it will not matter. Yeah, my point is that suppose both bulk have the symmetry G, and you want to connect them by a gap invertible domain wall, right?
So do you have two bulks that are SPT phases or SET phases?
Oh, any.
They do not have any symmetry.
Not any phases, and with symmetry too, but they are connected by one low-dimensional gap SPT, which is invertible as well. I think they will still be they still identify the phase on the two sides.
Maybe, but yeah, still on. But maybe we can chat afterwards, and you can explain to me what you mean.
I think we should move on.
Yeah. Okay. Cool. So, like if you want to show that a model is in a trivial phase, then well, you would construct an invertible domain wall to the trivial phase. So that's the same, like a domain wall to the vacuum is the same as a boundary, right? So in this case, the invertible domain wall becomes an invertible boundary. And one move, like defining an invertible boundary, is depicted here. So this would be an invertible boundary of a 2 + 1 dimensional path integral. And the move would be to kind of here you have like a thin tube with this like invertible boundary on the inside and the surrounding 3-dimensional bulk. And on the right-hand side, you kind of close this tube by gluing in a cylinder. And on the right-hand side, you kind of get the cylinder with the invertible boundary on the top and bottom. Yeah. Okay. So now I've been introducing these like topological invariant path integrals, and I've shown that like tensors obeying certain consistency equations, they describe topological phases at the fixed point. However, this doesn't really help so much if it turns out that like topological phases do not have such fixed point path integrals. And unfortunately, this is indeed the case to some extent. So what we find is that all known examples for topological path integrals, or for like any sort of fixed point model in general, all of these examples do only describe phases that also do have topological boundaries. And this kind of, in fact, one can like see this fairly easily, that this has to be the case if we take this like very simple form of the topological path integrals, where you just put one tensor at every tetrahedron, and like just contract indices between neighboring tetrahedra, and you impose topological invariance via Pachner moves. But all known fixed point constructions boil down to this simple type. So like from this you can see that you cannot have stuff that does not have a topological boundary, because for these like simple types of topological boundaries, you can always construct a standard like topological boundary. And this wouldn't be a problem if it would be the case that all topological phases always had a topological boundary. However, there is an important counterexample, and those are so-called chiral topological phases in 2 + 1 dimensions. So those are important because they, for example, they describe the fractional quantum Hall effect, which is one of the few topological phases that have actually been observed in experiment at all. So if we do want to be able to describe these chiral phases, then we basically got like 3 options. So one option would be to make a more complicated ansatz for a topological path integral, to like consider like some more complicated geometry of tensor networks associated to your space-time. This way you can in principle evade like existing no-go theorems, but still up to this point there's no example for such a more complicated like path integral capturing a chiral phase. So it would in principle be a possibility that is still open. Another possibility that we could do is we could simply take non-fixed point descriptions and work with those. So for example, we could consider a Kitaev honeycomb model, which in a certain parameter range captures a chiral Ising anion phase. And some of those models might still be exactly solvable by some other non-algebraic means. But that's not really a very general method, and that's not what we are going to look into for this talk. So for this talk, what we're going to do is we're going to look at some like studying these chiral phases by using some more high-level description. So we're not going to use a microscopic model, microscopic topological path integral, but instead we're going to use kind of some like sort of invariant of these path integrals without actually giving the path integral itself. And such kind of higher level descriptions, they can be obtained from a area of math that is called extended TQFT. And so here in this table, I give you some examples or I show you so these extended TQFTs, they come in different levels. And for the case of like 3-dimensional spacetimes, there are 4 of these levels. So let's start by looking at the lowest level. So the lowest level would have so-called 3-2-1-0 extended TQFTs, which would also be called fully extended TQFTs. So now these are rather complicated mathematical objects, and actually I don't think there's really a super like commonly agreed on definition. However, what they're supposed to do intuitively what they're supposed to do is they're supposed to describe actually microscopic models for topological order. So they're supposed to describe topological path integrals, like I introduced them so far. So instead of like trying to define this like complicated mathematical structure, which is this extended TQFT, for this talk, I will just say, well, kind of, why not just use a topological path integral as the definition of what I mean by fully extended TQFT. And one example for such a fully extended TQFT is given by this Tarai-Vero TQFT. So it's known that this Tarai-Vero state sum can be formulated as fully extended TQFT. And we know that this is just a microscopic model. So this seems to fit.
And I think you said earlier that topological path integrals are not capturing
Harrow phases.
Non-topological boundary.
Exactly.
Extended TQFT is supposed to fill that gap.
Yes, that was the point.
So the Tarai-Vero describes
yeah.
gap properties.
No. So this lowest level is the same as just having topological path integrals. So this will fail to that's what I explained to you so far, and this will still fail to capture chiral phases that have gapless boundaries. Yeah. Okay, so now if you look at the opposite direction, the highest level description, which could be called a free extended TQFT, but probably no one would actually call this a TQFT at all. This is simply a function which associates to every closed 3-dimensional manifold a number. And physically, what this number is supposed to be, it's supposed to be the contracted partition function of a microscopic model. So if you're given a path integral, then you would like microscopic path integral hypothetically, then this will just be the contraction of this path integral on a closed manifold, which is a number. So now these numbers, they are essentially, this map is essentially not constrained by anything. So for any connected manifold, you could just associate any number you want. So there's a problem because there's no reason why such a map should actually correspond to any microscopic model. And in fact, most of such maps just associate numbers. They do not correspond to any like topological path integral. And not even the opposite is clear. So it's like not even clear if like two models, microscopic models, if they are in different topological phases, if they would always associate different numbers to some manifolds. So in that sense, this is a higher level description, but it's not useful for anything. Okay, let's look at the second highest level description. This would be 3-2 extended TQFT, but this would be originally just what is called plain TQFT, so standard TQFT. So it's originally defined by Atiyah. And what this physically captures is the endpoint correlation functions of a hypothetical like microscopic model. And these endpoint correlation functions have to obey some consistency condition that come from the topological invariance of this hypothetical underlying microscopic model that isn't actually there. However, even with this description, it's still highly unclear, or it seems very unlikely that it is useful in the sense that there would be a one-to-one correspondence between such like sets of n correlation functions and actual like microscopic topological phases. So this still does not seem to be useful. However, there seems to be kind of one sweet spot in between, namely the so-called 3-2-1 extended TQFT, which is kind of the second lowest high level description. And physically, what this does there, in the previous level, we had like endpoint correlation functions, so we describe the phases using the point-like defects in space-time. What we have here is we describe the phases using the line-like defects in space-time. And those defects are precisely the onions. So what this means physically is describing a topological phase via its onion theory. And such 3-2-1 extended TQFTs are an example for this, or well, essentially all examples for this are given by so-called Reshetikian-derived TQFT. And those Reshetikian-derived TQFT, they are given by unitary modular tensor categories. And these unitary modular tensor categories precisely describe the onion theories. And so now it is very commonly believed in physics that onion theories actually classify topological phases, even though this is actually a highly non-trivial statement. And it's like unproven, but it's like an established fact, and this has been demonstrated by just many examples of microscopic models. So in that sense, this is still a useful description. And the good thing about this is that this description also captures chiral phases. Cool. So the goal for this talk is to like give you a simple definition of this extended TQFT, which is simpler than like this like mathematical framework of extended TQFT, but still does the same thing and is also very directly connected to the actual physics. And in order to give this the definition, let me first go a few slides back and let me revisit topological path integrals in a slightly different perspective, which I call the gluing perspective. So instead of considering like triangulations of a complete closed spacetime, and I consider like patches of this triangulation. So this would be like triangulations with a boundary, and I call this boundary the space boundary, and I call the interior of this triangulation like the internal triangulation. So now what I do for every such patch of the triangulation, I simply contract the tensor network path integral on this patch. What I then get is a tensor, and this tensor has this like path integral is open indices at the space boundary. So this tensor has indices that correspond to the space boundary. So for example, in 2 dimensions, you could take a patch of a 2-dimensional triangulation as shown in orange here. Then you take the associated tensor network as shown in black. And then if you contract this patch, you see that you get a tensor that has 1 index for every edge of this of the triangulation at the boundary. So now instead of saying we have a topological path integral given by a tensor network living in manifolds, we now say we define the same thing by saying we have a map from triangulated, like which associates to every triangulated manifold with boundary a tensor with indices living on the boundary. Yeah.
The lines inside, that's just notation, right? On the right hand side.
Yeah, sorry. Yeah, that's just some symbol to, yeah. Yeah, exactly. It's just represents some tensor. Yeah. Cool. Now, of course, if you pick an arbitrary such map, then it will actually not be a map that comes from a topological path integral. In order to ensure that this is the case, we have to introduce some axioms. And these axioms will have the usual form. So if M is this map which associates tensors to triangulations, and then we now consider different operations G that act on the triangulations, and we have different operations C that act on tensors. And now we want that these operations G are compatible with the different operations C via this computing diagram with this map M. And now there are three such kinds of axioms. So first, if we take two disjoint patches of space-time triangulation and we evaluate the path integral on these two disjoint patches, then what we get is just the tensor product of the contraction of the two individual patches. That means that disjoint union of like triangulations with boundary is compatible with taking tensor product of the associated tensors. The second thing is if we consider some triangulation with boundary and we take two simplices inside the boundary and we glue them, so that means we kind of bring them together and identify them, then the path integral on this glued triangulation, that will be just the original path integral without the gluing. Just now we have one more additional bond connecting the 2 points that have been glued. That means that if you contract the path integral on this glued like triangulation with boundary, this will be equal to the path integral on the original unglued lattice together with one more index contraction. That means that if we glue two simplices at the boundary, this will be compatible with contracting the two indices that are associated to these indices of the tensor. Yeah.
What's the time?
Oh yeah. All right. Yeah, I think I think because of the technical issues. Yeah. So yeah, I don't really need to get to the end of my slides. It's also fine. We can also stop at any time. Okay. Yeah. I try to speed up and cover at least some of the non-background stuff, and then we can let it be. Okay. Cool. So and the third axiom is just we take the axiom of topological path integrals, namely this invariance and Epachen moves, and apply it to our setting. That means that if we have two of these triangulations with boundary and we apply a Epachen move to the interior, then the tensor that we associate does not change. Okay. So instead of imposing this last axiom, we can also just change the domain of this map M. So because the triangulation of this interior manifold doesn't actually matter, but only the topology, we can just say now this map M associates tensors to manifolds with boundary, where only the boundary is triangulated. The interior is not triangulated. And then we can forget about this last axiom. We have left with like two axioms. So what I've done now is I've presented like topological path integrals with a slightly more complicated definition. So let's consider a simple example, like two-dimensional topological path integrals. So now I associate a tensor to every two manifold with a triangulated boundary. And gluing would look like this. As an example for gluing, consider this manifold on the left consisting of two disks. And for each disk, the boundary is triangulated with 3 edges. And now gluing 2 edges would mean to just bring them together, identify them, and what I would get is a single disk whose boundary consists of 4 edges. Now the gluing axiom would say that, well, to this left like thing here, I associate a 6-index tensor. So now if I take the 2 indices at the 2 glued indices and contract them, then I get a 4-index tensor, and this is exactly the tensor associated to that thing on the right. And another example for gluing would be to, well, I can also glue 2 edges that are near each other. In that case, if I identify them, this like vertex in between would just like disappear in the interior. So like in normal cases of gluing, topologically, what this gluing does is it attaches like a one handle between the 2 different things that are glued. But it could also be a more general operation. It could like attach any higher dimensional handles or also be some trivial topological operation. Okay, so now the structure, what we got is a map. And if you want to specify that map, you have to write down an infinite set of tensors that are associated to an infinite set of like manifolds with triangulated boundaries, which is inconvenient. But you also have an infinite set of axioms constraining them. So the way to handle this practically is, well, the reason why we can still handle this practically is because we can choose a finite set of generators and relations. So in this example here, it's clear that we can glue every of these manifolds boundary from a single disk whose boundary is decomposed into 3 edges. And it's also clear that like all the axioms follow from axioms that actually are like gluing versions of the Pachner move. And now we're kind of back to the topological pathing laws, and we see that this is actually just an alternative language of describing the same stuff in a slightly more complicated way. Okay, but this slightly more complicated language is actually the language that will carry over to also these higher level description of topological phases. And to show this, let me maybe give like the simplest example of such a higher level description, namely ordinary, what is called ordinary TQFT in 2-dimensional spacetimes. So these ordinary TQFT, they would describe like 2-dimensional spacetime, 2-dimensional topological phases via the topological point defects, or equivalently, as I said earlier, via the endpoint correlation functions. So now the thing I associate tensors to are 2 manifolds with embedded points. So instead of having manifolds with boundary, I have manifolds with embedded points. And so before I said this boundary, I call the space boundary. Now I call these points kind of space points. And the tensors that are associated to these things, I simply have 1 index for every point. And now I again have like this disjoint union axiom, that disjoint union of these manifolds with points equals the tensor product. And the more interesting thing is the gluing axiom. That means that if I glue 2 points together, then this is compatible with contracting the corresponding indices of the corresponding tensors. So this equivalent to what has been defined as like standard TQFT. If you know about standard TQFT, then there we actually associate tensors to manifolds, 2 manifolds with boundary circles. But this is equivalent. We just shrink every boundary circle to a point, and then we get this. But this language is kind of somehow slightly more physical. And also in this case, there exists a finite set of generators and relations, and the classification is something very, very well known. Namely, this corresponds to commutative Frobenius algebras. Okay, so based on this, let me try to distill a general scheme for defining stuff, which I call tensorial TQFT, based on the last 2 examples. So first, it's important to mention there's like not one kind of tensorial TQFT, but there's many different types of TQFT. And such a tensorial TQFT is a map which associates tensors to something that I call extended manifolds, which one can define rigorously. But for now, this is just intuitively a composite of manifolds of different dimensions. And some of these manifolds I call internal manifolds, and some of them I call space manifolds. The space part, the space manifolds are triangulated, the internal ones are not. I assign a tensor to every such like extended manifold, and this tensor has 1 index for every simplex of these space parts. And this assignment has to obey 2 axioms. One is that disjoint union is compatible with tensor product, and that gluing is compatible with, like gluing 2 simplices of this space, triangulated space part is compatible with contracting the 2 corresponding indices at these simplices. And this, like from all what I know of extended TQFT, which is like, I'm not an expert in this, so I don't want to make too strong of a statement here, but it seems to be like from all that like I know that comes out of extended TQFT, that this sort of structure of defining stuff captures all of that actually, and even more actually. So maybe let me show you one more example of such a tensorial TQFT. And this example will, like what will come out of this example is something you already know, namely, or might already know, namely fusion categories. And it will also be very similar to Levin-Wendt string net models. So the thing, the internal So now we consider three manifolds with boundary, but both the three manifolds and its boundary will be considered like internal stuff. So there's not triangulated and there's no indices living there. And the space parts will now consist of a network of one-dimensional manifolds which meet at vertices. And this network will be embedded inside the boundary. So physically, this type of tensorial TQFT will describe like topological phases in three space-time dimensions with boundary, and will describe them via the like one-dimensional defects inside the boundary. So you might call these boundary onions, even though they don't have any notion of braiding. So as an example for such a string net inside the boundary, you might consider like a 3-ball and then the boundary 2-sphere, and then inside this boundary 2-sphere. You might have a string net like this. Now the tensors you assign to those string nets on the boundary, they have one index for every string and one index for every vertex. And now these gluing axioms, they come actually into two different types. So one gluing axiom is gluing at vertices. So you can take two vertices at this boundary and glue them. That means just you kind of like bring them together and identify the piece of boundary of both of them. So if you would do that to two like vertices that live on different 3-balls, after gluing them, you would have a single 3-ball. So what happens to the string nets when you glue these is that you kind of identify those adjacent strings pairwise in a pairwise way. And then you just remove these fusion vertices and pairwise connect those. So the operations on the tensor side that this is compatible with is, first of all, we project to the space where all these string labels are pairwise equal. This is done by these delta tensors here on the left. And then we do just an ordinary contraction over these fusion indices. And now there's a second gluing axiom. And this now corresponds to, we can also glue at these strings, not only at the vertices. And this gluing of strings can be applied to any closed loop of a string. So this can be a contractible loop, but it can also be a non-contractible loop inside your two-dimensional boundary, if the two-dimensional boundary is non-trivial, if you want. And the effect of gluing such a loop with itself, basically, the effect of this is that this loop is removed from the string net at the boundary. But the effect to the overall topology of this three-manifold with boundary is that we attach a two-handle. That means like we consider this annulus-shaped region surrounding this string in the boundary, and then we attach kind of the side of a cylinder to this region. So if you would consider a loop winding around the inside of a solid torus, and you do this gluing in of the cylinder, then this would look like filling in this donut hole. And the operations on the level of tensors that is compatible with this, so you just sum over all these labels, these string labels A, and actually you have to consider a weighted sum, and the weight, this dA, is just some part that is also part of the definition of this type of tensorial TQFT. And we will see in a second that this tensorial TQFT is equivalent to like fusion categories, and then in this context, the dA is what is known as a quantum dimension. Okay, so now again, like the map as such is specified by an infinite set of tensors. So in order to handle it practically, we have to look for a finite set of generators and generating axioms. And we can find that like any such three-manifold with string nets and it's inside its boundary can be glued together from this simple one, which is a 3-ball. And inside the boundary 2-sphere of the 3-ball, we have like an embedded string that looks like a tetrahedron, like the one skeleton of a tetrahedron. And now this tensor associated to this has 10 indices, and this will just be the F tensor of a fusion category. And the one like axiom that generates all other axioms that will just correspond to the pentagon equation for this fusion category. So what these string diagrams are, they are essentially the same as the string nets in 11-Venn models, but presented in a very different way because, well, instead of saying that I have this F tensor and I can use it to deform string nets. I just say I have arbitrary string nets and I have these two very simple gluing axioms that I can glue at vertices, and I can glue at these ribbon loops. And then the F tensor just drops out as a generator from this from these simple axioms. What I also see is that like naturally, these string nets actually, so the amplitudes of these string nets actually depend on a three-dimensional bulk, which is usually not there when people talk about string nets, and that actually gives you some very powerful tools to consider different topologies of the three-dimensional bulk. Okay.
Sorry.
Yeah.
Are you going to Walker-Wang model yet? Is that part of Walker-Wang model?
No. Yeah, I probably won't get there in time to introduce Walker-Wang models, unfortunately. But yeah, let me maybe at least quickly go over another type of tensorial TQFT, which achieves what we wanted to achieve a few slides ago, namely to describe also chiral phases via this slightly more high level way. So here we take a tensorial TQFT that's very similar to the one before, just we do have just three manifolds without boundary, and the string nets, they're not embedded inside the boundary, but they're directly embedded into the three-dimensional manifolds. And actually one small detail that might become important later is that these in this general definition of these extended manifolds, one side effect of this definition is that all of these smaller dimensional manifolds always have a normal framing via these higher dimensional manifolds. So these strings are now actually ribbons, so they have a normal framing relative to the surrounding three manifolds. Okay. But apart from this, the gluing axioms are just the same. They have the same effect on the string diagrams. The operations on the tensors is the same thing. Just topologically, they do something different, because these vertices that I glue, they're now not at the boundary, but inside the three manifold, and there's no boundary. So gluing does not correspond to attaching one handle, it now corresponds to doing a zero surgery. So what that means is that I just cut out the two balls surrounding these vertices and then identify the boundary of these two balls.
C equals 0 is the chiral central charge. Chiral,
yes.
Chiral, not total central charge. Chiral.
Huh? So
C is chiral central charge, not total central charge.
Yeah, C is a chiral central charge. So yeah, the title is explained by the fact that what will come out here from this the general definition of a tensorial TQFT, what will recover, what you will find is a UMTC. But actually, for this first slide, I will miss something small, and then I will accidentally only have UMTCs for which a chiral central charge is 0. So the second gluing operation also looks the same as for these 11-event type string net fusion category TQFTs, but just now topologically, when I remove such a loop inside the interior, this corresponds now to a one surgery operation and not a two handle attachment of this three-dimensional manifold. So that means I cut out this solid torus surrounding this ribbon loop and I replace it by the dual solid torus. So it means I cut it out, in other words, and I glue it in back again after applying a modular S transformation to the boundary of this torus. Okay, and we can also glue at individual points of the three manifold, which is well, it's not a consequence of the topological invariance of the model, just follows the fact that we want robust topological phases where the ground state degeneracy on a sphere is equal to 1.
S0 there is 2 points. S0 there is the boundary of V1 or 2 points.
Yeah, so you can
S0 is 2 points.
Yeah, exactly. Okay. So this is the surrounding of yeah, cool. Okay, now we can again find generators and relations. Two generators are given like that, and they exactly correspond to the F and R tensors of the unitary modular tensor category. The axioms are, well, one axiom that exactly looks like a pentagon equation, another axiom which I have to pick it here, which corresponds to the hexagon equations, just different ways of gluing these like generators together, which yield the same result. And then involves like 3 of these R tensors and 3 of these F tensors. If you write them out in terms of indices, you see it's the same as a hexagon equation. So now we got now these tensors restricted by pentagon and hexagon equation are known to define a braided fusion category. However, these axioms so far, they do not imply all other axioms. There's one axiom more, namely to this end we consider a 3-sphere with 2 embedded loops, which are linked with each other. And now we consider 2 copies of the 3-sphere, and we glue one, like a pair of loop in each copy. So we haven't actually defined what it means to glue 2 loops, but this can actually be, well, this can actually be emulated with the gluing operations that I presented you earlier. And what it means is we just like cut out the solid torus surrounding each tube and each of these loops, and then you identify these boundaries of a solitary. So if I perform this gluing, what I get is the manifold I get is S2 times S1, and I will have like 2 remaining loops, and these 2 loops are embedded in this S2 times S1 by they're just both winding around the S1 part. Okay, so now if I view this like Tensorial TQFT as a braided fusion category, then the tensor associated to these 2 linked loops would be just the S matrix. So it's like a tensor with 2 indices corresponding to with 1 label at each loop. So it's a 2-index tensor, so a matrix. And this tensor here associated to the right-hand side, this has to be equal to this is 1 if the 2 like labels are the same and 0 otherwise. Physically, this follows from the fact that the ground state determinacy of 2 anions A and B on a sphere is like 0 if the anions are different and 1 if they're the same. But actually, we can also motivate this purely from the axioms by the fact that well, like if you look at these axioms, then 0 is always a solution, and you want to rule it out. So you want to rule out subspaces that are entirely 0 because they are kind of boring, and that's a way of exactly doing that. Exactly, and so if you look at what this like gluing move implies in terms of tensors, then we get that this means that like S times the stagger is an identity matrix. So this S is a unitary matrix, and that's exactly the condition that makes the braided fusion category into a modular. So we've seen that by just imposing these 2 simple gluing axioms, we do get out braided fusion categories, but actually this modularity condition just simply follows from these gluing axioms, and which themselves directly follow from the topological invariance of the underlying model. And at this point, usually like people are making lots of physics assumption, like that kind of each anion has to be detected by some other anions. So in this picture, we don't need any assumptions, just follows from the topological invariance. Unfortunately, that's not the end of the story. So there's even one more axiom that does not follow from all the axioms so far. And to this end, we consider a loop inside a 3-sphere that is twisted once. So the loop is a ribbon, and the twisted ones means that we go around, and this normal framing rotates by a 90 degree. So if we apply this gluing axiom to this loop, then what we get is a 3-sphere. So that's just a effect of topology. I actually can't explain that to you why that is, but that's just something I found in some topology textbook. And if you look at the corresponding equation that this corresponds to, then if this like d times theta over caps d, if this is the tensor associated to this twisted loop, so the theta is just known as the topological twist of the anion A. So this is the weight associated to the tensor, and if you do the contraction, then you have to sum over all these like labels, and the tensor, the scalar associated to the 3-sphere on the right is 1 over d. So if we define our chiral central charge in the common way, and it's commonly done, then this condition just implies that the chiral central charge is 0. So that means that this tensorial TQFT unfortunately can only describe phases with a 0 chiral central charge, and yeah, so like
0 mod 8.
Yeah, it's yeah, this way defines the central charge only mod 8. Yeah, and we want to fix this because these are exactly the chiral models for which we are going to this more high-level description. For the non-chiral models, we can also do the microscopic models. In fact, there's a small gap here. So there are phases that do not have a topological boundary, but still have the C equals 0, and they could already be studied in this framework, but not in the microscopic framework. So in order to fix this, what we do is we just introduce a 4-dimensional bulk for the 3 manifolds. And then like all the axioms and gluings are the same, except for that topologically, every surgery of a 3 manifold is like now becomes a handle attachment to the 4 manifold. And this way we can avoid this anomaly freeness axiom, because now if we consider both sides, then there will be just 2 different bulks on both sides. So specifically on the left side, we would have something like a complex projective plane with a 4-ball removed, whereas on the right side, we would just have a 4-ball. So on both sides, the boundary is a 3-sphere, but we have different bulks. So this equation does not longer hold. So we do not need to have the chiral central charge is 0. Unfortunately, that problem also arises for the modularity. So in this equation for the modularity, also the bulks will be different on the right and left side. And so now we are back to braided fusion categories, which we also like know that they do not describe onion theories. It's something else. So in order to solve that problem, we now introduce an additional move that these assignment of tensors invariant under, namely arbitrary surgery operations of these 4 manifolds. So equivalently, we just say that these tensors associated to the 3-dimensional ribbon graphs with this 4-dimensional bulk, they only depend on the cobordism class of the 4 manifold, but not on its topology. And we can also show easily that this dependence is only up to a prefactor, up to a global phase. So they actually don't depend very strongly at all on the 4 manifold anymore. And if you do that, then modularity is restored because, well, simply the 2 4-dimensional bulks on the left and right hand side of the equation, even though they're not the same, they are in the same cobordism class. However, these anomaly freeness assumption, this is still broken because, well, CP2 is known to be like the one 4 manifold that is like non-trivially in oriented cobordism. So every oriented 4 manifold is equivalent to n copies of this complex projective plane under surgery operations. And but this complex projective plane itself is not. So that means that the 2 sides here of this equation, the 2 4 manifolds, they are also different cobordism classes. So that's why this anomaly freeness condition is still broken. And this is why we exactly get UMTCs if we assign this 4-dimensional bulk that is invariant under surgery. Okay, so now it's pretty late, so let me just jump to my conclusion slide. Unfortunately, we won't have time to cover any Walker-Wang stuff, but it's fine. So I've defined here a general framework of what I call Tensorial TQFT. This is a map that associates to like every extended manifold a tensor. These extended manifolds are like composites of manifolds of different dimensions, like manifolds boundaries and maybe ribbons and strings and so on. And they have some space part that's triangulated and to which we assign indices. So these indices are the indices of the tensors assigned. Then I have 2 axioms, namely that gluing equals contraction and then disjoint union equals a tensor product. And if I consider like microscopic topological path integrals, they correspond to such tensorial TQFTs where the space part is the boundary. But this tensorial TQFT stuff can also describe more high-level stuff, which like roughly corresponds to 3-to-1 extended TQFT. In this example, the space part is given by ribbons embedded inside the 3-dimensional manifold. Now the indices of these tensors associated to the ribbons and not to the boundary. And this way, if we also take care of this so-called chiral anomaly by by also associating a 4-dimensional bulk, which is, however, only an important optical Bodism, then we get out the usual classification of topological order in terms of the onion theory, so in terms of a unitary modular tensor category. And so now how we would get Walker-Wang models is to just like take this map which associates tensors to 3 manifolds with ribbon networks at the boundary of a 4 manifold, and to densify this map. That means to construct from it a map that like associates tensors to triangulations of 3 manifolds at the boundary of 4 manifolds. And this way you get the Walker-Wang model, and this way you can also show that you can disentangle Walker-Wang models. Okay, let me stop here. Thanks for listening, everybody.
Thank you very much. Any questions from the audience or from the online attendees? Could you just maybe say a few words about the Walker-Wang conversion since you skipped that? That's a good topic. You have those slides. Maybe.
Oh yeah, maybe I can very quickly go over it.
Because that's the main part of the talk, right? You didn't present
So here, so well, we know that a topological path integral in 4 dimensions, which for space-time dimensions, which Walker-Wang models are, they are supposed to assign tensors to triangulated 3 manifolds, which are at the boundary of 4 manifolds. So now the way to obtain this tensor associated to this like 3 manifold triangulation is, well, we just take a dense ribbon network. So these networks of ribbons, intuitively, should think of these ribbons as being like microscopically long. But this like triangulation lattice, this is actually something microscopically small. But now I just put no one can like disallow me to also put this ribbon network on something microscopically small. And this is what I do. I just like take the ribbon network doing a dual to this 3 manifold triangulation. And then I take the tensor that the braided fusion category assigns to this ribbon network. And then I have to show a couple of things. I have to show that if I want to glue to like tetrahedra of this 3 manifold triangulation, then this can be emulated by the gluing axioms of the braided fusion category. But this is pretty simple. So if I glue 2 tetrahedra, then I can just like glue the vertices at the center of these 2 tetrahedra, and this will do the same as gluing these 2 tetrahedra of the topological path integral. However, if the 2 tetrahedra share a common face, then if you glue them, you will like end up attaching a 1 handle to your 4-dimensional manifold with boundary. But you want the gluing of 2 tetrahedra at nearby tetrahedra to be a topologically trivial operation. And along this 1 handle, you will actually end up with a ribbon loop winding along it. And at this place now, you apply this gluing axiom for ribbon loops. And this will precisely remove this 1 handle. So that means that using both the vertex gluing axiom and the loop gluing axiom of your braided fusion category, using those 2, you can exactly emulate gluing tetrahedron of this like 3-dimensional triangulation. And that's a very like short way of like defining the Walker-Wang model. And if you apply this like to also define boundaries of the Walker-Wang model, then you can easily see that like for unitary modular tensor categories where this like bulk 4 manifold is invariant under surgery, this directly implies that this Walker-Wang topological path integral itself in 4 dimensions is invariant under the same type of surgery, if you define it that way. So that already means that the Walker-Wang model is invertible, but it doesn't yet mean that it's in the trivial phase. For this, you have to define an invertible boundary. And the invertible boundary can be found by very similar ways. Yeah. Cool.
There are other slides you don't want to show. Other things.
I mean, I
other
do.
questions, comments?
Yeah.
That's the one handle.
No, so this is just if you do want to define Walker-Wang as a state sum,
So
then
on the right hand side is the one handle.
no, there's no like handle shown here. This is just if you want to define the Walker-Wang model in the state sum language, then you would want to assign a tensor to every 4 simplex of your 4-dimensional triangulation. And in order to get this tensor, like the boundary of a 4 simplex is a triangulation, it's a 3-dimensional triangulation. So now you take the ribbon network, which is dual to this 3-dimensional triangulation. And you just simply use your Tensorial TQFT to evaluate this ribbon network to get a tensor. So that if you embed it into the planar slides that I have here, then you then this ribbon network would explicitly look like that. And so you evaluate this ribbon network, and this is the tensor associated to this 4 simplex, in which defines this 4-dimensional state sum. And the state sum is also known as the Cranietta state sum. Yeah.
Okay. Other question, comment? There's I think Hank. Go ahead, Hank.
Yeah. Hello. Can you hear me?
Do you hear us?
Is the audio maybe not working?
I can hear you, but can you hear me? Hello? 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 My microphone is on, but
Yeah, go ahead, please.
Okay.
okay, so you can hear me now?
Yes.
Can you hear me now? Okay,
Yes.
okay.
Yeah. Yeah.
Okay. So thank you for the nice talk. So can you say a little bit more about the relationship between, like, there's this particular construction in which you have an input of a fusion category or a braided fusion category, and outputs a fusion 2 category, which is like the condensation functor that Davide and Theo has constructed. So can you say something about how your construction is related to that?
So okay, if fusion 2 category could be defined in this framework by, so here is associated tensors to ribbon networks that are embedded in 3 manifolds, but I could also consider like networks of ribbons and membranes that like are between these ribbons. And so if I associate tensors to such things, and the 3 manifolds are at the boundary of a 4 manifold,
right,
then this would correspond to fusion 2 categories. And now you see very easily that like braided fusion categories are just a special case of fusion 2 categories, where these like labels that are associated to these membranes, they are always trivial. So there's only one label. I think maybe in the category theory languages, people would say there's only like one object or something like that.
I see. Okay. Okay, I see. Yeah, because at least morally, what you just described seems to be very close to what, like, physically the condensation functor is doing. Essentially, it's adding all the membrane operators that condense to the boundary stuff that it's encoded by your given fusion category. Yeah, so I was just wondering, because I think Walker-Wang is actually an example of that.
Yeah, exactly. So Walker-Wang models are not the most general type of topological path integral in 4 dimensions that has a topological boundary, but they're only one specific subclass, and the general type of such models would be given by these fusion 2 categories.
You also you also mentioned modularity, so I was just wondering, like, maybe like your claim is that there's a particular construction which takes in like modular categories, and then it, I guess, spits out a modular 2 category, because that, I think, is actually that structure is I think still under investigation.
So I don't actually know what a modular 2 category is exactly, so I can't really answer, but you can do something. Well, I mean, there's like multiple way you can write a tensorial TQFT that might capture the what you call a modular 2 category. So you might either take this construction, go 1 dimension up. So you might consider like ribbon networks, like networks of ribbons, vertices, and membranes inside 4 manifolds, which are at the boundary of a 5 manifold, and this 5 manifold is only defined up to cobordism, and maybe that would correspond to a modular 2 category. I don't know.
Right. Yeah. Yeah. Okay. Great. Thank you.
Thanks for the question.
So probably there's another question. Still have another question, or probably gone. Any more question? There was one earlier. Okay.
Cool.
Yeah, no, that's thanks, Andrea. Thank you again. Thank you very much.
Thanks for listening, everybody. Sorry for the technical